Bismillahirrahmanirrahim. Assalamu alaikum dear students. Welcome you all in lecture 11. In lecture 11 we are basically dealing with the same topic that is we discussed in lecture 10. And lecture 10 basically we in lecture this is lecture 11. This is lecture 12. Sorry, this is lecture 12. And in this lecture 12 basically we cover the same topic which we done in lecture 11. So, okay. So there is a numerical on that problem, and you have to check that equation. Okay? What is the numerical? They say that you have simply supported beam having a span of 18 feet and a total load that is 9 kg per foot. Okay? And remember that the bar is whenever you are placing your simply supported beam on the support. Okay, this is your simply supported beam. You know, okay, this is your beam. So they assume the moment from this mid point, clear? Okay, they assume the moment diagram from this point. So basically they say that this is the zero movement point, clear? And the bar is extended from this point towards the support side is for a distance of 6 inches. That is the LA distance, clear? We consume a lot of time on this LA, clear? So that is the LA distance. LA distance is that distance which we take beyond the point of inflection. Okay, a distance is that distance which is taken inside the positive movement region. Okay, inside, this is the positive movement region, so that is a, and the extension beyond the point of inflection, that is a. So your LA will be equals to 6 inches. Clear? Now this is the cross section. This cross section has two number 4 bars, and I think the number 4 bar area 2.14 square inches roundabout. Okay, I think so, roundabout this one. Diameter is 1.69, clear? And this is the effective depth, clear? So first of all we will determine LD. Okay, so the spacing of the bar is given in the example, clear? The spacing is given, that is U stirrups having 10-inch center to center, and this 10 is also less than d by 2. So your this is greater than 10 inches, so your ACI stirrup criteria is also fulfilled. So stirrup criteria is fulfilled. Now we will just check the clear distance between these two bars, that how much this distance. If this clear distance is greater than dB diameter of bar, so then it will be case number 1 in table number 81. So you need to visit the development lectures. In that lecture, inshallah, you will see table number 81. Clear? So there are two cases basically, case 1 and case 2. So the present is relating with the case number 2, because if you calculate this distance will be greater than diameter of bar, because this distance is obviously 16 minus side cover is 1.5, so 2 into 1.5, because side cover on both sides, and as the bars are stirrups around number 3, so you add 0.38 for the stirrups dia, plus you have also to subtract 2 bars of number 14, that is I think so 1.69. So if you do this calculation, you will get 8 point something. Clear how much it comes out to be? It comes out to be 8.87, which is greater than dB. So this is clearly case number 1 from table number 81. Your development and formula will be this one. And you must remember psi t, as it is not top reinforcement, so your psi t, there is a bottom reinforcement, psi t equals to 1. There is no coating, so therefore it is equals to 1. So just putting the values, you will get 80.2 inch is your development length. Now you will check it. Clear? For LD, now you see that as in lecture 11 we did this step, that if you are drawing that tangent, with the actual moment diagram, okay, so this moment capacity is Mn, and this moment capacity you will get at a distance of LD. Clear? You will get that moment capacity at a distance of LD. Now you will determine this moment capacity, and there are two bars. Okay, so your A will be A SFY divided by 0.85 FC prime into B. Clear? So S will be 2 multiplied by the area of this number 14 bar, Fy is 60, 0.8, FC prime 4, and B is 16. So putting these values you will get the A value, and the A value will be 2.25 is the cross-sectional area of number 14 bar, 60, and you get 4.96 square inches. Sorry, you just, because I already mentioned you that at this M is basically determined on the basic formula A is Fy into D minus A over 2, because this is the actual movement capacity diagram, not it is the actual movement diagram, it is the movement capacity diagram. Movement capacity diagram is constructed on the basis of this formula. So phi will be dropped, A is Fy D minus A over 2, you will get Mn, okay, which comes out to be 80 kips inch. Clear? Now what will be the shear at this point? What will be the shear at this point? So as it is a UDL having simply supported edges, so you know that their reaction will be at support, reaction will be equals to Vu. Clear? And Vu will be, if it is Wu, that is 9 kip per foot. Clear? So Wu L divided by 2, this will be the shear. So this shear will be WL divided by 2, which is 81. Clear? So you will just, and remember that this is the simply supported case, so you have to multiply 1.3. Okay, so 1.3 Mn divided by Vu plus Ln. Clear? And 1.3 divided by the 6 is added. Okay, clear? 6 is added because it's the actual form. 87.5. So hence 87.5 comes out, okay, which is greater than LD. So this check of ACI will be clear. Okay. Here it says basically that the number 14 bar is unavailable in a market supplier, so you need to investigate 6 number add bar. You need to did the calculation for 6 number add bar. So if you place 6 number add bars in the beam and you check, you will get the clear spacing comes out to 1.25 inches, which is more than 1 inches. Clear? So your clear spacing is more than diameter of bar. That check is also fulfilled. And how much, and you use the table F5 to find that the minimum width for 6 number 14 add bar will be 5.5. As you have 16 inches, so there your minimum width is also okay, which is for this to check the clear spacing. A15 table A15 of this book, at the last pages you can see that this is table F5. Okay, so if you are providing number 8 bar having 6 total number of bars, you need to be minimum 15.5 inch width. Clear? Minimum. Then your spacing criteria means your clear spacing will be more than diameter of bar. So as we are providing here 16 inch, so our width is at this point is okay, because 16 inch exceeds this one, the bar spacing exceeds deeply, and the beam has a code minimum shear in this case. Same case is that because 10 inches is more than, because the depth is same 23 points, so your minimum spacing criteria of steel is also okay. So this is case 1, not case 2. Okay, now compute the same development length formula. Okay, this only and only dB will be changed, not other parameters, because there in the previous calculation is 1.69 and in the present calculation it comes out to be 1, because the diameter of the number add bar equals to 1. So your development length reduced. Okay, if you are, if your this criteria is not fulfilled, you need to decrease the size of bar. Okay, because when you are decreasing your size of bar, your development comes out to be decreased. And now you have need to solve to find out MN for 6th number add bar. Clear? So you just need to determine A from the same formula, but here your AC will be changed. Your AC will be 8, no, your AC will be, you have 6 bars, 6 multiplied by the cross-sectional area of number add bar. I think so that is 0.7 square inches. So you will get, AS. So putting that AS in there, in this point, all thing is same, you will get the A value and then again put that value in MN equation. Clear? A is Fy into D minus A over 2. Clear? And that S will be this one. Clear? The value which you get from this, you will just put here, and Fy is same, you will get Mn, and Mn will be 5370 kh. Putting the values, you will get 92 point, and hence again your LD is less than 92. So that check criteria is fulfilled right now. Okay. So this is example, just giving you a little bit information that how we use that check. Okay, of ACI. This is the effect of discontinuities at bar cutoff points and flexure triangle. I already mentioned a lot of things about this topic. Okay, and I already mentioned you that we will use these 3 checks. Okay, and one must be satisfied. So we did this in coming example. Clear? Now we comes to Nelson book and we solve this example. Clear? And this is a very interesting example, a very broad example. It will take a lot of time. Okay, so we need to inshallah cover this example. We have a lot of time. Okay, so let's see, start it. This is integrated design of T-beam. Okay, it's a T-beam, and you have to design and you need to provide the cutoff points. Okay, so you see that you have a floor system consists of single span. There is only one single span. T-beam at feet on centers. The T-beams, there are 3 T-beams and they are placed a center to center distance of 8 feet. Okay, 1, 2, 3. Okay, this is longitudinal view and this is sectional view. Clear? So if you draw the plane of this beam, so you can understand it that you have a room. Okay, you have a room like this. Clear? And there are T beams. One is there, one is there, and one is there. Clear? And the center to center distance of these T beams are kept equals to 8 feet. Clear? This is 8 feet, this is 8 feet. And there is a little bit cantilever portion as well. Clear? And you must know, oh sorry, there are 3 beams. Yes, 3 beams. So the total span of this beam is 10, 10, 20, 26 feet center to center distance. Clear? This is center to center distance, and okay, supported by 12-inch masonry wall. Okay, the beams are supported on at 12 inches. Clear? This width is basically 18 inch. Clear? But they considered center to center distance for a, this is total 1 feet, this is total 1 feet. So what where, suppose 12 inches, sorry, this is 12 inches, sorry, this is 12 inches, therefore 12 inches equals to 1 feet, clear? So, and 25 feet clear span inside the inside, clear? This is clear spacing is basically 25 feet. No, clear spacing is 25 feet and center to center spacing is 26, because point 5 is from this side and 0.5 from that side, clear? The general arrangement is shown in figure. A 5-inch monolithic slab, thickness of this slab is basically 5-inch. Monolithic, okay, means at one time the beams and slabs are placed. So uniformly distributed service live load, this is service live load. The T-beam, in addition to the slab load and their own weight, must carry a 16,000 pounds equipment applied over the stem of the T-beam 3 feet from the span. There is 2 concentrated equipment load, you see there 16 kips, clear, which is right on the center T-beam at a distance of you can say both these loads are 6 feet away from each other and 10 feet from the center line of the beam to from the center of the support, okay, 3 feet from span, okay. 3 feet from the span center line, okay. As shown, a complete design is to be provided for the T-beam using concrete of 4,000 and 60,000, because normal wet concrete and uncoated reinforcement, so your lambda and psi e will be equal to 1. Lambda will be dropped from the calculation for shear and bond, and psi e will be dropped from the calculation for bond, clear? So you must need to understand the example, clear? Okay, this is the example, this is the UDL, okay, and you have first of all computing your all types of weights. So you have a 5-inch slab, okay, what will be their weight, and you see you have equipment weights, so these equipment's weight will be worked like a live load, so it must be added with live load. So what will be your ultimate load, clear? So you see that according to the ACI code, the span length is to be taken as the clear span plus the beam depth, but need not exceed the distance between the center of supports. This is the ACI criteria for span length. Now, because you see that whenever you are using WL square by 8, your effective, what will be your effective span, okay? So how much your that length, that is known as effective length, and that effective length starts from basically ACI code says that your span length is basically equals to your clear span, okay, that is for 25 feet plus 1 depth, that is the effective depth of beam, clear? Now, but this is called span length, but it must not be increased than the center to center distance between the supports. The center to center distance is 26 feet. So if you add these two, 25 plus effective depth, it must not be increased to 26 feet. So as your depth, the effective depth is basically which is assumed 1224 inches. Estimating the beam width dimensions to be 1224 inches. The calculated and factored dead loads are to be, so your effective depth, you can say if you provide 3-inch clear cover, it comes out to be 21 inches. So if you add 21 inches, which comes out to be, which is more than 1.6 something, so 1.57 something. Okay, so if you add, let's say that is 2 feet, so you add that, it comes out to be uh, 27 feet roundabout, which is greater than 26 feet. So your span length will be this one. You have to use 26 in your calculation, not this one. Okay, so your slab weight will be 5 feet, sorry, 5 inches. So if you, if you are interested to get the weight of your slab, just divide your thickness in a, I mean that just only convert your thickness to feet multiplied by weight, that is the normal weight density of concrete, 150 multiplied by the 7 feet. Now from where this 7 feet comes, okay, for this you can, you you need to understand your plan. Clear? Remember that the width of this beam is equal to 1 foot. Clear? Now this beam will taking a slab weight which is, you can say, which is the half of this span. This span. Clear? The beam will also have a width. Okay, this beam also having a width. So this width. This is the total. You can say this is the total uh, slab area. The half span, the half slab area are loading. Comes to this beam and comes to this beam, and the rest will go to this beam, and the rest will go to this beam. Clear? So there will be a little bit loading on this beam, but greater load will be present on this beam. Clear? So if you divide, you have to find out the width of this and the width of this. Clear? So this width will be how much? Center to center distance is basically equals to 8 feet. So just subtract zero point 0.5 from that side and 0.5 from that side. You need to neglect this beam width, because this beam width will be taken in the calculation of beam width calculation. We will considering, because if you see that this is the beam cross section. Clear? If this is the beam cross section, and there is slab on the top of this T beam, so we will consider this whole web. Clear? We will consider this 24 feet 24 inches width. So this portion of slab which you are seeing right here will be counted in when we are calculating the width of the beam. So if there is another T beam, clear? Okay, if there is another T beam like this, clear? So how much load will comes to this beam from your slab. So you just need to divide your slab into equal parts. Okay, and the one part length will be up to this distance. This width is basically 1 foot. Okay, now the center to center distance of between these two consecutive or successive beams is 8 feet. So how much will be this clear distance between the webs of the beam? Clear? This will be 8 minus this half width of the beam, that is 0.5, sorry, and this half, that is 0.5. Clear? This is 0.5 and that is 0.5, because 1 feet is total, so divided by 2, this is 0.5. Clear? So 0.5 comes out to be 7. So 1, and subtract 1 from 8, it comes out to be 7 feet. So 7 feet total slab, and just divide that 7, because half loading of span will comes to this beamer, and half loading of slab will comes to this beam. So we are calculating the loads on the center beam. So there is also another beam. Clear? There is also another beam. So there, this half slab dimension will be now 7 divided by 2, which I think 3.5. And similarly from that side, okay, this is 3.5. So the total slab load, okay, comes from 3.5 plus 3.5, which equals to 7 feet. Clear? Which comes to be 7 feet. So one center beam will take in a load from 7 foot wide slab. Okay, 7 foot wide slab. Clear? If I draw this diagram more clearly, so you will understand it more in a better way. Okay. So you see here that this is the met beam, T beam. Okay, this is its width is basically equals to 1 feet. And this dash line is the basically tributary area for this beam, and the width of this tributary area from one side is 3.5 and from the other side also 3.5. So the total width comes out to be 7 feet. Clear? So therefore they take 7 right there. Clear? This 7 is comes out to be basically uh, from that tributary area. So it comes out, this is the dead load, 440 pounds per foot. And now this is the basically the total web area. I already mentioned you that here we will draw that slab portion. Clear? This is the total, and most of time in our calculation when we are dealing with T-beam design, we just take the web depth in calculation of beam width. But here they take the total width. Okay, they consider the slab portion as well. Okay, this is 12. Okay, so 12 multiplied by the whole depth, that is 24 inches. Clear? So therefore this 1 foot, 1 foot is dropped here. Clear? And they just only consider the 7 feet. They add this 1 foot in there in the calculation of width of the beam width. Okay, so 12 multiplied by 24 is clear. Dividing by 144 to convert this square area into square foot, and multiply by the density gives you 300 pounds per foot. Add these two, giving you 740 total dead load. Okay, now 1.2 multiplied with factor 1.2 gives you factor dead load, that is 890 pounds per foot. The uniformly distributed live load which is given, okay, 165. Now it multiplied with 8, because here if you see they take the total width of the tributary area, that is 8 feet, not dropping 1 foot. Okay, here you take the 1 foot because you are calculating live load, not dead load. Okay, so means that the total live load will be distributed over the whole span. Clear? Whole span, that is coming out to be 8 feet. Clear? Not you are dropping 1 foot here for live load. So this is 1.165 multiplied by 8, giving you 1320 pound per foot, and 1.6, this is live load factor, multiplying it with this one, 1320, you get this one. Clear? The factor live load is, the factor load will be WU 1.2 dead plus 1.6 live load. Clear? It comes out to be 3 kip per foot. Now this is the UDL, and with the UDL you have two equipment loads that are concentrated loads. So the equipment load will be live load. Okay. So 16,000 pound multiplied 1.7 1.6 factor, you will get 25,600 pound. Factor loads are summarized in figure 6.5. Here you can see this diagram. Clear? This 3 kips per foot board. This is your factored ultimate load, and 25.6 and 25.6. These are the equipment factored load, factored live load. Clear? And these point loads are placed from the center of support at a distance of 10 feet. Both are according to the distance of 6 feet and 10 feet. Clear? Now we need to draw the movement diagram as well as the shear force diagram. Okay. In lieu, or you can say instead of other controlling criteria, the beam width dimensions will be selected on the basis of shear. Now, whenever you are selecting your beam dimensions, their width and their depth, so you have, three criteria. Okay, from those three criteria, you will select your beam width. The first one criteria is basically, your deflection criteria. Okay, so if you have a simply supported beam, your H minimum, as we did in calculation of simply supported beam whenever we are designing with a rectangular beam. So I think so it is around about L by 16 multiplied by 12. Okay, this is deflection criteria. You have criteria number 2, and in criteria number 2 we consider our depth from row provided should be greater than row minimum, should be less than row max. From this criteria you will find out our required width, and that is a very famous formula will be used, that BD square uh, comes out to be, I think so, mu divided by phi e rho into, here I'm forgetting that formula, but it is somewhat like 0.59, I think so, fy into rho divided by fc prime. You must need to search out this formula in your design of rectangular beam calculation. So from there you fix your width, and this row is basically fixed. This row is basically selected in between row max and row minimum. So it will give you the minimum and maximum value of your depth. Okay. So the depth which is selected from this criteria will pass this check. Clear? And you have no tension about this check as well as your depth. Okay. So it gives you minimum depth and maximum depth. For row max and row minimum, you will determine two values of depth. You select the depth value in between these two values, so your minimum depth criteria will be fulfilled. And the other criteria is shear criteria. So in this, basically you need a sufficient depth for to support shear. Okay, to support shear, because if you are providing your stirrups, so there is restrictions on stirrups, that your stirrups must not be placed more than 3 inches or 4 inches or 2 inches. There are minimum ACI spacing criteria, because if you are stirrups are so much closing, their placing of concrete will be difficult. So if your spacing, if your depth is is less, then your spacing of stirrups will close. Okay. So if you so we need to check these three criteria. Okay, so shear criteria must be fulfilled, because the that whenever your BS, once we calculate the shear, so if it is greater than 8 phi into FC prime into BW into D, so we need to revise our cross sectional dimension, because shear is so much, you can say, so much high. So in that case we need to revise our dimension. So basically, um, your depth should be such that your BS must be less than 4 P FC prime into BW. Clear? And you have, basically, when we are designing our footing, so we check this depth from beam shear as well as from punching shear. So here basically the depth criteria is satisfied from shear. The left and right reactions under load are 25.6 plus 3 multiplied by 13, 64.6. If I draw this diagram in SAFE, and I will analyze it, so you can see that how much shear is exists in this point and exists in this point. So let's see that what are the results. Clear? Mm, Basically, this is the shear force diagram for half span. Okay, and you know if I draw this diagram, if foot is okay, we have a beam, clear, having one span, a length of, you can say, 26 feet. Okay, and let's see. Clear. uh, let's see, check it. Okay, and this one is, you must know that you have to assign these supports, although there are beam on the level of uh, slab, where the slab is placed on the wall. So these beams, although it may assign, these joint may be assigned like fixed support, but here they are assigned basically uh, simply supported. Clear? Because the span is so much high and the loading is so much high, though, so those beams just didn't work like a fixed support. Clear? So let's see. We assign the frame load that is distributed, and as we calculate the self drag, so taking self multiplier is equals to 0, and we have 3 kip per foot loading. Okay, and let's see, this is 3 kip per foot loading. And we have also 26 and 26 point loading. So let's say this is, we assign point loading, dead load force, at a distance of 10 feet we have 25, I think so, 25.6 kip, and then at a distance of 16 feet we have, the first is 10, the second is 16, we have 25.6 add with existing, okay, to that. So let's see, analyze it. Model do not run, and run it. Okay. Saving is a T-beam, okay, and save. So if we draw the shear force diagram, okay, so this is shear force diagram. 64 and 64 caps. You can say this is the maximum shear at the support. Clear? So basically, this 64.6 is the maximum shear which is applied at the supports. Clear? And then there is a jump and it comes to 0. Clear? So basically, this 64.6 comes out from that reaction. Clear? With the effective beam depth estimated to be 20 inches. Now, the maximum shear that need to be considered in the design is, now we need to, you need to consider critical section, critical shear. We almost considered critical shear, okay, and that critical shear, it lies at a distance, if it is a face of support, and this is your shear diagram. That this is 64. That so your critical shear lies the distance of distance d, okay, effective distance d. There is your critical shear VCR. That it lies the distance of d. Now, what is our effective depth? So, at effective depth, using similar triangle rule from SET, you can easily determine. So, by similar triangle rule, you can say that 64 divided by total distance, that is, I think so, 13 equals to this VCR divided by 13 minus this d. So, you will get VCR. Okay, that will be the critical shear, and this shear will be used in the shear force design. Clear? In the strip designs. Clear? You need to recall your shear design. Okay, how we did shear design. I don't want to waste my time on shear design. Clear? You people need to recall those theory, and from there you can learn that how we design shear. So your critical shear comes out to be 58.1. Clear? This minus 3 0.50 plus 1.67. It is a critical shear. It is considered to be, although the ACI as this is the ACI criteria. I already mentioned you. Okay, your VS should not be greater than this value. I already written this. Okay, and your VS should be less than this one, but should be less than this one, or your VS should be less than this one. Okay, these are the this this is a lower, this is a lower limit. This is a lower limit, and this is the upper limit. Clear? So, we will adopt it. We see that is the sharing capacity of the concrete. It is almost taken as 2p FC prime BW into D, and Vn basically, mm, Vn basically, that I clarify some point, okay, because you people will be confused. Okay, so here V is taken equals to 4 into FC prime. If you take here P value, then you have to multiply P. If you don't take P value, then you not need to put P value here. Okay. So BD clear, and your VC, that is the shear capacity of your concrete, it is taken as like this. Your nominal shear Vn, that is the nominal shear capacity, it is equals to Vc plus Vn. So if you add these two, you will get your nominal shear will be equals to comes out to be 6 into Fc prime Vw. This is your nominal shear capacity right now. Clear? So I think now you will understand, okay, that from where this term comes. So from this criteria they calculate your depth. How? Leaving the depth at their place and shifting these three terms to the left, we can get V and divide by 6 Fc prime into Bw. Clear? So Bw will be given that is 12 inches, okay, and Fc prime is 4006 and Vn, this is the nominal shear, and you may consider it 58. That is the, you can say VCR, critical shear, okay. So they consider VCR divided by 6 into 0.75. P factor is basically used here, clear, to to calculate a more safe value, clear. So dividing by P gives you 204 square inches plus sectional dimensions will be BW will be fixed, that is 12 inches, and D will be 18 inches. Are selected, provided a total beam depth will be 22 inches. The assumed dead load of the beam need not be revised. Now, you see, from your shear criteria, your effective depth comes out to be, from this shear criteria, your effective depth comes out to be 18 inches. And in the design, we take D is equal to, I think so, that is 20, because our overall depth is our overall depth is our overall depth H is 24 inches, clear. So if I assume 3-inch clear center to center concrete cover, my effective depth will be 21 inches. So as 21 inches is more than 18 inches, so now we are at the right safe side, clear. So we don't consider this value, okay, we continue calculation on this safe value, clear. So this value will pass the shear test also, clear. So we are on the safe side, okay? So this is cross-sectional dimensions, okay, from shear criteria selected, provided. So providing a total depth, this is H. Now from shear criteria, your H will be 22 inches, and we selected are basically we are using 24 inches. Okay, we are using 24 inches, so we are on the safe side. The assumed dead load of the beam F, if this value is more than the assumed value which we will assume in the initial calculation, that is 24 inches, this one. Where it is, okay, 24 inches. So then we will revise our calculation. We will revise our beam width for that value which we get from shear criteria. Now 24 is more than 22 inches, so therefore we don't need to revise our calculation. Okay? And you should remember that 18 inches and 22 inches. Now they use now this dimension. Okay, they use now those dimension, that is 22 inches and 18 inches, which is getting from shear criteria. But at the initial stage, we basically assume 24 inches. Okay, so it don't make any kind of difference. Okay, you calculate the loads for heavier depths. Okay, and you are providing lower depth. So this don't make any kind of difference. If you are calculate the loads for lower values and you are using higher values of depth and width, then it is unsafe. If you are using lower value of depth and width and your calculation is basically on the basis of higher value, then you are on the safe side. Clear? So we can make this kind of calculation once we don't know about the width and depth. Okay, so if you don't know about the width and depth of beams at the initial stage, so you can assume higher values of width and depth and make calculation. Calculation means you will determine the watts and then check it, cross check it. If you are cross check like this 22 inches, so if your cross check means that your values which you calculate from your shear criteria is less than from your assumed, so your calculation is okay. If they are greater than, so you have need to recalculate the watts for the values which you are get right now. Okay. अगर सिंपल बात में मैं आपको बताऊं कि अगर आप लोग इनिशियल स्टेज पे बीम की वेट और डेप्थ को आप एज्यूम करें और इस एज्यूम डायरेक्शन वेट एंड डेप्थ पे आप लोड्स कैलकुलेट करें, ठीक है, कोशिश करें कि ये वैल्यूज आप ज्यादा लें, ठीक है। नो आपने एज्यूम डायमेंशंस पे आपने बीम की वेट को कैलकुलेट किया, ठीक है, बाद में आप इन डायमेंशंस को चेक करते हैं। जब आप इस डायमेंशन को चेक करते हैं फ्रॉम शेयर क्राइटेरिया, जो भी क्राइटेरिया है आप यूज करते हैं, तो अगर उस क्राइटेरिया से आपके जो वेट्स यानी जो डायमेंशंस आते हैं वो आपके एज्यूम डायमेंशन से कम है, so your calculation is okay, you need to proceed your calculation further, okay। लेकिन अगर ये वेट और डेप्थ जो है ये कम आ जाए, सॉरी ज्यादा आ जाए फ्रॉम योर एज्यूम, देन अगेन जो डायमेंशन आए वो आप यहाँ पे पुट कर दें और फिर आप न्यू वेट्स कैलकुलेट करें, तो फिर आपकी कैलकुलेशन ठीक होगी। एंड वन थिंग रिमेंबर कि यहाँ पे हमारी जो कैलकुलेटेड वैल्यू है वो 22 इंचेस और 18 इंचेस है। आज जो हमने एज्यूम किया है 24 इंचेस, तो 24 की जगह आप 22 इंचेस यूज कर सकते हैं, ठीक है, और ये इससे कोई मसला नहीं होगा, ठीक है। इसी तरह वेट हमारा कांस्टेंट है क्योंकि वेट के ऊपर फिर स्पेसिंग का वो असर पड़ता है। सो लेट्स सी, दिस इज आवर क्रॉस सेक्शन, ओके, दिस इज आवर क्रॉस। इफेक्टिव डेप्थ इज यूज्ड एज 18 इंचेस, क्लियर। Okay, so up to this point, up to this, up to this limit, I think there is no problem. Okay, these all are the shear design. Okay, and you people must need to know about this because you are at the last stage of your PhD design. So these are just only the initial steps. Once we make flexure design for our beam, then we make shear design for our beam, and that is, I think so, in chapter 3, chapter 4. They are in full detail. So you people just need to revisit those calculations, and this is nothing. This is easy steps. Okay. Now, according to code, the effective flange width B is the smallest of the three quantities. These quantities will be used in a T-beam design. Okay. How much your effective width of your T-beam, because we have a flange width, okay, of T-beam. Now how much that flange width will be, okay, this flange width, which is known to be B effective, clear. This is B effective. So these B effective is determined from three criteria, and those three criteria, I think so, in T-beam design analysis is clear in chapter 3, chapter 4, okay. So you must need to revisit those three criteria. The first criteria is 16 HF plus BW, I think so. BW is the BW. This is this way, correct? This is web width. Okay. So this one criteria is used. Okay. 16 HF is the flange width. That is 5 inch. Clear? This is flange width. That is 5 inch. Clear? So 16 multiplied by 5 gives you 18, and BW is 12 inches. This is 12 inches. Clear? So give you 92 inches. And this is another criteria. This is criteria number 2. There are different criteria will be used for beam design. So 2ln divided by 8 plus bw. 2ln is the clear span. That is one. Uh, Here it takes, okay, let's say 26 inches, but almost I think it is a clear span. Yeah. So putting the values gives you 90 inches. And there are also some other criteria, center to center distance and center to center, and span by 4, like that criteria. Okay. So there are criteria. You need to revisit your chapter number 3, chapter 4, I think so. In that chapter, you can visit these criteria. There are some criteria which is used for T and LD design. Okay. So you need to check those criteria. From those criteria, now you have to select from those criteria the minimum value. That will be your plan value. Be effective. And they select that. This is also a criteria. Okay. Center line beam spacing. Okay. I mentioned you that be effective. This is for be effective. Okay? 3 or 4 criteria will be you need to check it. Okay. So center to center distance is 96 inches. So this will be the controlling value. Yeah. This one will be the controlling value because this is the most minimum. The second controls in this case the maximum movement is a mid span here. Okay. Now okay, you have to select, okay, now 90 inches. Clear? And thus your maximum movement you can get WL square by 8. It is for simply supported, you know, and 25.6 multiplied by 10. Basically the beam is divided into, you can say, into 2 portions. Clear? The beam is basically divided into 2 portions. The one is for UDL. Clear? At one portion they consider UDL, that is 3 K per foot, and the length is 26 inches. Clear? And in another criteria, in another portion, it considered 2 point loads, that is 25.6 and 25.6. Clear? So 25.6. Clear? So the distance is 10 inches. Okay. 10 foot, sorry. And then the distance is 6 feet. So I think your maximum movement will be somewhat here. Clear? So this distance, if I assume this distance is x, so from there your maximum movement mu will be directly, you can say, wu l square divided by l. But there you have to determine your mu. Like this reaction is, I think so, 64.6. So 64.6 multiplied by at the midpoint, because this is a symmetry case. So they basically use what, this one. Okay, so 64.4 multiplied by this half distance, multiplied by this half distance is 10 plus 3, that is 13, I think so, and plus this one 25.6 multiplied by 3, it gives you that. So add these two loading, you get the maximum. If you comes to the shape and you draw the maximum, uh, if you want that, how much will this one. So from directly you can say that this is your maximum loading, which just at the right, at the center, it will be at the center, it will be at the center, that is your 50 at. Okay, it will be in the center. Clear? And from shape you can get these things very easily. Clear? right there you can it will this will be 510 foot kip, although there is 2 kip difference, but it is nothing. It can be uh, taken. No, there is not great difference there. So basically this is your maximum movement, and then inshallah we will design in the next lecture 13. Up to this point I think so it is enough. In lecture 13 inshallah I will start the rest of calculation from this point. Okay, so I think it is enough because the time is going on from 1 hour. So if you have any question you may ask. Claire, welcome.